Okay, let's start now. So, today we'll be doing week 7, and it will be both the theory part and the problem solving. So, first, like in this week 7, we have major two topics. So, one is scan and another is disability. So, we'll finish one topic, do some problems, and then we'll start another topic and do the problems on that. So, this is how we are going to go about the session today. So, let's start now. Okay. Week 5 and week 6, we have looked at the regression problem. But now moving forward from week 7, we are going to look at the classification problem. So in classification problem, again, we have this input data set um, where the features are x1, x2, so on till xn, and these xi's are in RD. Right? I mean, the uh, features are same, but where in regression problem, my label could have taken any uh, value in R. Here, there's a difference here, right? So for these yi's, y1, y2, so on till yn, this so these xi, which were the features, these yi's are the labels. So if these yi's belong to R, I knew that was a regression problem. But here, uh, from week 7 onward, we are going to talk about the classification problem. So these yi's are taking some discrete values over here. So mostly we'll be looking at the binary classification problem. So these yi's will belong to 0, 1, or you can also say like they belong to -1, 1. Okay, meaning depending on what your labels are. Okay. So majorly we'll be talking about we are looking at all the algorithms in the classification case where we have two labels, right? So we are calling such problems as binary classification problem. For example, if you have the spam, differentiating the email as classifying the emails as spam or non-spam comes under the binary classification problem, right? So things like this. And whatever we'll learn for the binary classification problem, it can also be extended to the multi-class classification problem. All right. So what is the setup for this binary classification problem? So our data set is this, right? We have these x's and we have these y's. So in general, we have this x1, y1, x2, y2, so on to xn, yn, where my x's belong to RD and my y's I'm taking here as 0 and 1. Okay. So we have two labels, 0 or 1. So as in the regression case where like our goal was to learn a model and given any new feature vector, we wanted to predict the label Y for that particular feature, right? So again, the goal here is same. We want to build a model where the model takes the input as xi, and give us a it should predict whether the label is 1 or the minus 1, or the label is 0 or 1, right? So again, what we want is, so again, our goal is to learn such a function h, which takes the mapping from RD, which and maps it to 0 comma 1, right? Uh, so like in the regression case, we had seen that once we learn this models, right, we need to know how good the model is. And for that, we had this notion of sum of squared error, and we wanted to minimize that sum of squared error, right? So the minimum sum of squared error we get, we said that such, that would be ideal for us. Now, similarly, in this case, uh, like in the classification problem, like how do we define the loss here? So their integration, it was sum of square error. Now, what is loss in this case, in the classification problem? So in the classification problem, we have the 0, 1 loss. So how do we define this as? So loss of H would be, so number of the fraction of data points which are incorrectly classified. That would be the loss here. So if there are total of n data point, so 1 divided by n, and you need to take all those data points and add those for which my h of xi is not equal to yi, right? So what does this mean here? This is my indicator function, okay? This is my indicator function. So it says if this is true, I will take the value of this function to be 1, this indicator function to be 1, and what is there inside is false, then it will take the value as 0. So here, this true statement is h of xi not equal to ya. So for all the features for which my h of xi, whatever my model predict h of xi, if this is not equal to ya, that is the true label, I am going to give the value 1. And for the features for which my h of xi is equal to ya, I'm going to give that value as 0. So the loss of h is basically defined as the fraction of data points which are incorrectly classified, right? So this is how we define the loss in case of classification. Uh, but now the problem here is that um, again, like we are not going to look at all the functions, like set of all the functions, um, like which are set of all the
Excuse
functions
me,
and
ma'am.
the loss. Yes,
Why take
yes, tell
1
me.
by n?
What? What is 1 by
Ma'am?
n?
Yes,
What?
ma'am.
No, no. This loss is sum over indicator of h of xi not equal to y divided by n.
Oh, okay, ma'am. Got it.
Okay. So if you have some points,
N is the total number of
n
data
is the
points.
total
No?
number of data point. Yes.
Then it means the summation, whatever
Mm-hmm.
we are indicated function is giving, it
Mm-hmm.
will be always less than this, no? Because always it will give either
Less,
1 or 0. Either 1
less,
or 0, no?
less than what? What is less than what?
Less than n.
This one, right?
This summation will always
Uh,
be less than 1 because the indicator function will give either 1 or 0. We are not considering 1,
uh,
it will consider 1 only if it is not equal to y level.
see, if it can mean the loss. This value. It is quite possible that all whatever model we have learned, it is predicting all the data point wrong. So in that case, it will be n, no? In that case,
It
this
will be n,
value
the value,
inside,
then the loss will be 1.
then in that case, the loss will be 1.
What does it mean geometrically or physically? If the loss is 1, then what does
Uh,
it mean?
so the loss is 1 is, it means this model is not. I mean, the model that you have learned is not good enough, right? It's not good.
Srikant, you lost everything. That's it. It's a
Yeah.
percentage, 100% loss.
Yeah.
Just
Okay.
percentage. You can take it as a percentage, a ratio, proportion. If
Okay.
it is
Lesser,
zero,
lesser,
thing is,
lesser the loss,
am I
greater
right?
the accuracy, right?
Yeah.
Mm.
Yeah, correct.
Okay. Okay. Fine. Okay.
Yeah.
Okay. Ma'am. Correct.
Okay.
Please.
Um, yeah. So again, like we are not going to look at the set of, I mean, we are not going to look at all the functions. Again, we are going to restrict as for the functions which are linear. Okay. So we will restrict this to this space of function where we'll define H linear to be set of all functions for which my h of wx h of wx is given by sine of w transpose x. Okay, so this is how this linear function is defined. Now we'll be restricting this loss to that linear function. So now what the goal is that you want to minimize this loss, right? And this loss is given by, so indicator of hw of xi not equal to yi, where I is varying from 1 to n, and this hw belong to h linear is what I will say. Okay, so this is our goal. We want to minimize this loss. Now the problem here is that this is an NP-hard problem. Okay, so this is an NP-hard problem, and because of this, because this is an NP-hard problem, it's difficult to come up with it's difficult to find an H for which we can say, okay, the loss is going to be minimum for this H, right? So, like to deal with this, we are going to look at many different algorithms for the classification. And in this week, we have started with two very simple algorithms. So the very first algorithm that will be seen in this week is the KNN, which is K nearest neighbor, and the second is decision tree. So,
Could you elaborate
uh,
on this? The NP hard means it is very difficult to decide.
yeah,
And
NP hard, like I mean, it's very difficult to find out a line which will separate my data set into two parts, basically, right? Uh, so this is a classification problem,
if
and
if we run all the data
mm,
points here with the function
mm,
SW of xi, then it will decide
mm.
whether indicator function will give the value.
No,
You will
see,
decide it. And how
there are
NP hard is
see
we are
there
saying.
see it's a binary classification problem. We are taking binary classification problem here, right? So it's
Yeah,
either zero or one. The label
yeah,
is either zero or one.
yeah.
For right.
Yeah,
So if it's such a case, then I mean I know there can be various possibility. I mean there can be various such function can be given for which this holds, right? I mean it separates my data set, that line separates my data set into two halves. But again, which one gives you the least is quite difficult to figure out. Because see, this is just going to take the value either 0 and 1, right?
yeah,
So
yeah,
this is more like a function which is which is not differentiable. So if
yeah.
this
It
is
is
not
not different. This function,
differentiable,
because the value is zero one only,
how will you
neither
find out?
continuous nor differentiable. Yeah.
Yeah, so it's difficult to figure out like what is that ideal edge that we should go for. Okay, so I mean this is an NP hard problem. It is quite difficult to solve. So like to deal with this NP hardness of this classification problem, to this loss that we have, There are various different algorithms that we are going to study throughout um, from week 7 to week 10. We are going to look at many different algorithms through
Okay.
which we can solve this binary classification problem. Okay.
Okay.
So the simplest algorithm that we will be looking at that we have for the for the classification is this KNN. Okay. So what happens in so what is the full form of KNN? This is basically saying K nearest neighbor, right? So in K nearest neighbor, like what we say is like if you have so we're first looking at K nearest neighbor. So in K nearest neighbor, like you let's say you have a bunch of data points and um um, so let's say you have some data point and you like it has two label 0 and label 1. Now if you are given any new data set, let's say some X test is there. So let's say this is my X test. Okay. Then I need to, if someone gives me this data set, I need to figure out what label should it predict or like what label it should be assigned to, either +1 or 0, right? So 0 or 1, right? So what are we going to look at here? What we are going to look at here is which point is closest, like this point is closest to which point basically, right? Which label more closest to. And ideally that should be, that is the label that it should be assigned to. But when we only look at one data point, like maybe let's say this is the closest, okay? For example, let's say this is the closest. Then just looking at one data point again is not good. So what we are doing here is that we are looking at this X test and we are seeing what is the closest uh, label from this test data point. So in this case, we can just look at one neighbor which is closest, and we can say that okay, I will assign it as 0. But again, the problem with just looking at one neighbor is that it is quite possible that that neighbor is outlier, and in that case, you will end up assigning a wrong label to your data set, to your data point, right? So that like that is not very ideal to do, not a very ideal thing to do. So what we can do is we can look at some k closest neighbor, k nearest neighbor. Okay, so again, we are going to do the same thing. It just if depending on what k you take, right? So if I take k to be 2, it means I'm going to look at two closest neighbor to this data point, right? And whatever is the majority, I'm going to assign that label to my data point. So that is the only thing. So what we do here is given um, given any X test, given a test X test, you find k closest neighbor. So let's say the k closest neighbors are x1 star, x2 star, so on till xk star. Okay. Now what you will predict is if you have to predict this label for X test, that is going to be like whatever the majority of the labels are. So corresponding to x1 star, you will have the label y1 star. Corresponding to x2 star, you will have the label y2 star. Similarly, corresponding to label xk star, feature xk star, you will have the label yk star. So whatever is the majority, so that is the label you are going to assign your X test to, right? So that is, it's a very simple algorithm. That's
We
all
will,
we do here.
we will assign only one, na? For X test.
What?
Only one level will be assigned. Na?
Only one label. So X test is either going to
Majority.
be 0 or 1. So when we say majority of this, it means, let's say, um, these were my K closest neighbor, these Xi stars, okay? Now, maybe my Y1 star was, for example, let's take K to be 5. So maybe my Y1 star is 1, my Y2 star is 1, my Y3 star is 0, my Y1 star is 1, and my Wi-Fi star is 0. Okay. So
Okay.
if I have to find the label for this X test, predict the label for X test, what will I predict? I am going to
One.
see that okay, out of five, three are one. So one should be a good answer here, right? So I will predict Y test
Equal
to
to
be
one.
equal to one here, right?
Here
That's all.
we took only on the bunch of the red point also. We can take up the green points also, no? Because the nearest may be that also.
No, no, I'm just
X.
explaining here. I mean,
But we
um,
can take in the nearest maybe out of all these data points, either 0 or 1. We can
mhm.
take some of the 0, some of the 1 also, no? The nearest.
Correct, correct. I mean, I was just telling what is this idea of K
Hello. Okay.
nearest neighbor.
Not only one side, both
Yeah,
sides
yeah,
we can take.
yeah, yeah. So here, I mean, if I see maybe this is
Uh,
close, this is
Practically, we will do
close,
all. We will practically
this
do
is
all.
close, right?
Mm.
Yeah, I mean, it's not necessarily that your data set will look like this, no?
The
I mean, this
closest
is just
means,
one example. It's going to be all scattered. It can be in
yeah,
some pattern, right? And in between, you will
closest.
have some. So maybe I'll draw a different picture.
Yeah, yeah.
Uh,
You mean K closest means we will decide first by going to the all the data points. Suppose X text point,
hmm,
a data point is coming, then we have to decide K closest by going through the all the data points and to calculate the distance. Okay, then only
yeah,
closest
correct,
will be decided. Then only we will be deciding the closest, no? And
correct,
then we
correct,
will
correct.
choose. Right? No, okay.
Exactly. So let's say this is the data set that look like. We have two labels. Maybe
Hmm.
red point indicates 0
Actually,
and
we
blue
have the only
indicates
method to decide, no, closest, the
correct,
distance,
correct,
right?
correct.
Okay.
Exactly. So let's say I have some excess to be here, right? This is my excess.
Mhm.
Now, if I say find five nearest neighbor, using five nearest neighbor, predict the label for this point. So
Mhm.
if I look at this picture, maybe this one is this one is this. This is also closer. This is also okay. So let's say this
Yeah.
is the one.
Okay.
So the maximum is blue one, right? Maximum is this blue out of five.
First,
So
in
I'm
the
going to
first
label it
page, we
as
will decide the closest, and then we will decide the majority of that by calculating the labor, right?
yeah, yeah.
First, we will
First, you need to
process
calculate the distance of this point with all the data point.
all the
Okay,
data points. Correct.
all the
Yes.
data point. You need to calculate all the data point. But again, one more thing here. I mean, just by looking at the figure, I mean, yeah, it is somewhere. Um, but what also happens here is that see, if you have a data point, you need to look at its distance from each of the data point, right? Then the very first thing you need to be very clear what distance metric are you using. Okay, so that is one thing. You need to define your distance metric, and then you calculate depending on what distance metric you have used. You calculate the distance of that data point from all the test data point to all the data point. And then, depending on your K, you will take that majority vote and decide your label. This is what is going to happen.
How do you select
Okay.
this value of k? Is there any method of
This is
optim
again this is again cross validation.
like k should be 4 or 5 or 3? How do you know?
Again, it is based on cross validation. I mean, you cannot just say this is idle K. This is a hyperparameter, right? This is something which you are giving your model. This is a hyperparameter.
This is our goal to find it out which one is better, right?
No, no, I mean, K is, yeah, you perform the cross validation, and then from there you can decide, okay, this K is suited for this problem. So K is a hyperparameter.
Some example will also come after that, because in the whole
Example,
whole
I'm going to.
whole, whole chapter will not having an example.
Mhm. Yeah, I will give questions.
Okay. Okay.
Okay. Um. All right. So here K is a hyperparameter. All right. So um. Okay. So these are the two things, and then what is also what can also happen here is like if the data set is small, it's okay that if you know the what distance matrix you are going to use, and data set is small, still you can go ahead and compute its distance from each and every point. But in case the data set is huge, then in that case, it's going to be very expensive. This um, process of finding the distance and then taking the majority vote and predicting going to be quite expensive. So that is not a very good thing, right? So again, this is a very simple model,
Can
and
you just explain the K hyperparameter means? What is
what
means by hyperparameter?
what is meant by hyperparameter? So see,
Yes.
hmm, I'm saying it's not K hyperparameter. I'm saying K is a hyperparameter here. So hyperparameter meaning like this K is not you're passing this K into the algorithm, right? So your algorithm only says that you have a bunch of data point with you, and if you have to predict the label for a particular point, you are going to look at the majority vote depending on what K you have decided, and then you are going to predict the label, right? So K is something that you will figure out using this cross validation technique, and uh, and based on that, you will decide K and find the label. This is something you're passing into the algorithm, right? By using the cross validation technique.
Yes, ma'am. Understood. But my question is, what is the meaning of hyperparameter?
Yeah, hyperparameter means any parameter which was not a part of your algorithm. Okay. I mean,
Okay, understood.
you're passing it,
Yes, ma'am.
you're
Understood.
passing it to the algorithm.
Can we say, when the hyperparameter is predefined before starting the modeling? Is it fixed before that?
No, right? I mean, you train your model, then based on the
It
validations
is
that
not.
you have, you
It is not
perform
a
the cross
calculated.
validation.
It is not a calculated value. It is prefixed value.
It is
And
not a
then we test.
prefixed value. It is not a prefixed value. Using when you have this validation set and you perform the cross validation, you look for different values of K, and then you see which works the best for your problem. So it's not something I would say is predefined. I mean, in the question, if you're solving some numerical problem,
Predefined,
of
I
course,
mean to say, not predefined. I mean, we have to prefix before starting the validation. The K is required to start the validation process.
no, you will check for a set of K, no? I mean, you cannot
Setup K,
fix
yes.
something.
Setup K. And for
Hmm.
each value of K, we have to test which K value is good. We have to choose, right? Is it
Yeah,
so?
yeah, yeah,
Right.
yeah.
Okay. Okay. Okay.
Madam, one question here. If you change the
Hmm.
value of K, so
Hmm.
K is say 2, 3, 4, 5, etc. Will the result
Hmm.
change? Will the
Uh,
result, like the majority value, the prediction value change, or it will remain the same? It should change,
See,
na?
hmm, it should. it should change. See, K you will decide based on like the lowest validation error that you get, right? So for whatever K you're getting the lowest validation error, I would say that is my that is the K that is going to that we're going to give the algorithm. That is what we're going to give to the algorithm, right? So depending on what K you choose,
Mhm.
your label will of course vary, no?
Level will vary, but you will calculate the error, and whatever is the least error, so that K will
That
actually sustain.
yeah, that K would be used.
Will be the final decider.
Huh,
Okay.
right. Okay. So this was, I mean, it's a very short, it's a very small algorithm, very simple algorithm. So I will discuss few problems from here. Let me share my screen. Sorry. Yeah, so this is a peer deck slide, and there are some 8 questions. Uh, Maybe if you want, you can join this. You can go to joinpd.com and just write in this code. You should be able to view this. Okay, nobody has joined yet. Okay, 2 students have joined. Um, so if you want, you can join this. Go to joinpd.com and use this code. You should be able to see. You should be able to give the answer over there also. Okay. So oh, okay. Let's start. So this is a very simple problem over here. The question says you have this binary classification task for which we use the Manhattan distance. And all these points that you see, they are located at the integer coordinates. So these points, so this plus sign that you see over here, this is 1 comma 1, this is 1 comma 2, and so on. Now the point marked in blue color is the test point. So the question is, if we use the Manhattan distance to calculate the distance between these points, then what is going to be the predicted label of the test point for k is equal to 1? This is the question.
Manhattan distance means the absolute distance, no?
Manhattan distance is absolute distance, yes.
Ma'am, the answer is 1.
The answer is 1. Mm, yeah. Okay, so this is very simple problem. So what you have to do is you have this test point with you, and this test point is basically 3 comma 2. So you have to find the label for predicted label for this test point when you're using k to be 1. So I'm going to look at one closest neighbor, right? So in this case,
2,
I'll go to the
2 will be
solution.
the closest.
Yeah, right. So I calculate the Manhattan distance. So 3 comma 2, the distance of 1 comma 1 from 3 comma 2, it's going to be 3. This is 2. So you calculate all this distance, and we see the closest is your this 2 comma 2. And 2 comma 2 has the label given to be plus. So I'm going to predict the label for my test point to be 1. So 1 is the correct answer. Okay, so this is the second question. It says, suppose we have a binary classification data set with
Madam, ma'am,
1,000
go to
data point.
previous, ma'am. Go to slide
Okay.
here.
Mhm,
Three to Manhattan distance we calculate for the each of the point. And go to the graph in the question.
mhm.
Can we do like this? Because this point 3 2, the visually it is we are seeing that the 3 plus points are nearest to
Mhm.
this. Can we decide on this basis also?
No,
Geographically?
um, see, Manhattan distance is different than the Euclidean distance, right? So Manhattan distance is like you take the absolute values.
Yeah,
I mean, the
difference of
different
both. Yeah,
absolute values.
yeah.
And then you see, and that's how you calculate the distance here. In this case, yes, it's turning out to be, I mean, the closest one from here, I can see this
Three,
plus one
three,
is the
three.
closest.
Yeah, three. Closest one
Two,
plus one.
three, two is the closest that I can see.
Yeah.
But and it turns out that even the Manhattan distance, this is the closest, but it is not always the case.
Okay. Yeah.
Yeah.
We cannot decide on visually. If it is visible also, we cannot decide, right? We have to calculate the distance, right?
Uh-huh.
Mhm. Okay. Okay, ma'am.
Yeah. Okay. So this is the second question. It says, suppose we have a binary classification data set. So you have 1,000 data point consisting of 600 points belonging to class 0 and 400 points belonging to class 1. If we use k nearest neighbor with k is equal to 900 to predict the class label of a test data point, what will knn predict?
0.
0.
Yeah, 0 is correct. So is it clear to everyone why 0 is the right answer? Is it clear to everyone why 0 is correct?
Please
Ma'am,
talk.
can you please quickly explain? I didn't understand
Yeah,
why.
please.
Yes, ma'am, clear.
Yeah, please. Please explain, ma'am.
Okay,
Which
see,
test?
mhm,
Mhm.
it's coming. Hmm.
It will go as per the majority, is it? That's what it means.
Yeah, so see, you had 1,000 data point, and
Okay.
out of
I mean,
1,000,
are you saying that the distance from the 600 points to 900 points for each data
no,
point? Distance.
see,
Okay.
600 data points has the label as 0, okay? And
Yeah.
400 data point has the label 1, right? So what we are saying is I am given an excess and I'm going to use 900 NN, okay? So K that is used is 900. Second is quite big. I mean, ideally it's not like that, but okay. This is a theoretical question. So if we use K to be 900, then what should my model predict? What should this KNN predict for this X test, right? So you see, like even if let's say, I mean, for this X test, maybe all the 400, I mean, all these points that are labeled as one, they all are coming in, let's say, these 900. Okay. So even if all these uh, labels, if all these points which are labeled as plus one, they all are coming in the 900 neighbor, still you have to take consider how many you have to consider remaining 500, no? And I know that they are going to be I mean, zero is the majority, and again still 500 are going to have the label zero. So my model should predict for k is equal to 900 to be 0. So 0 will be the right answer over here.
Got it,
Is this
ma'am.
clear? Yeah. Okay.
In this question, if k is say 200, what will be the answer?
If k is 200, then there's nothing that can be said for sure, right?
The k has to be more than 400, isn't it?
Uh, Not really. I mean, see, k,
If say k is 500, what will be the answer?
okay, if k is 500, then in that case, it can be anything again. So maybe in 500, all the plus one label are coming. So 400 are taking those only. And only 100, there are 100 points for which the label is 0, right? So in that case, I will take the majority as 1. But what happens if in 500 all are marked as 0? Then I will take it as 0. Here, this distinction is coming because of this k, taking k to be 900.
So
Right?
if k is 600, then it should be 0.
If k is 600, not really again, no. See,
Then
k is 600 meaning what? K is
Yeah.
600 meaning if I have a test data point, I am going to look at 600 closest neighbor, right?
okay.
Okay. So if may, let's say in this 600, if I get in this 600 neighbors, if I get all the 400 neighbors which are labeled as positive, labeled as plus one, then I am left with only remaining 200, right? And then 200 will come from 0 and 400 will come from 1. Then in that case, if k is 600, I should, based on this, I should label it as 1. Why will I label it as 0?
If you take the other way around, say
Okay.
if
If you take other way down, then of course it will be 1. But just using this, the information that is given to us, that you have 1,000, you have a data set with 1,000 points and 600 are labeled as 0 and 400 are labeled as 1. And if you give me k to be 600, of course I cannot say anything for sure, right? There, it can be anything. It can be 0, it can be 1.
that's why
But
600
here,
will not be able to predict at 600.
it's not able to predict. Here it was 900, so the distinction was there that okay, whatever happens, the majority is going to be 0 here. I mean, the label 0 here, because even if all the out of 900, even if all the positive labels are used, still I need 500 data points, right? And the majority out of 400 and 500 is going to be those 500, which is labeled as 0. So it will always predict it to be this 0, label 0.
What is this 900 is the number
Hmm.
of data points or the number of
No,
comparisons?
900 is, see, k, I'm saying k is 900, right? So what
What does
is
it
k?
mean?
K is how many neighbors you're going to look at.
It means
How
that
many
the
nearest
test,
neighbors are you going to
yeah,
look at?
the test data which is coming, we will compare with the 900 nearest neighbors, right?
Yes, exactly. That's what I've drawn here,
And
right?
and out of this,
So if you have a test data set, I'm going to look at 900 neighbors,
yeah, and out of six
right? I'm going to
1000,
look
we
at
will compare,
900 neighbors.
yeah, 900.
Hmm. So out of
Then
1,000, I am,
how yeah, how we will choose this 900? Either we should take 400 or 600 or 500 here and
No, no.
100.
Here the question is not about how do we choose K. Here the question is if you are given a data set which
Yeah,
consists of 1,000 data points, where 600 are marked as negative and 400 are marked as positive, and
yeah.
if I want to perform a K nearest neighbor to predict the label for the X test where K is equal to 900, then what should my model predict? That's all the question is here. It's not about how do you find K. Okay,
A K is
it's
already
about
given, na? A
K
test
is
data.
already
Suppose,
given. Exactly.
suppose, suppose there is a test data. Then we will have to find whether where this test data will go, right? Either in the 400 or in the 600 group, right? Is
Correct,
it?
correct. Yeah,
This
yeah.
is the question.
That's all the question is. Yeah.
Then, because we don't have the value of the test data, how will we measure the distance?
See, it's not about measuring the distance. That's what I'm saying. No. See, the question. See, you have 1,000 data point. Okay, you
Hmm.
have 1,000 data point. Let's say this has 1,000 data point. Now,
Yes,
out of these 1,000, I am saying
400,
the labels. These labels are
600. Yeah,
there are 600 of such points, and
zero mark.
there are 400 of such points. Okay,
Hmm. Hmm.
400 of such points. So this is
Hmm.
labeled as 1 and this is labeled as 0,
Yeah,
right?
correct.
This is labeled as 0. Now, let's say I am given a X test. Okay, I'm
Yeah,
given a X test.
yeah.
Now, if I'm given an X test, I want to know if I am using 900 NN,
And
meaning I am going to use K to be 100. I'm going to perform the K nearest neighbor algorithm where K is equal to 900.
yeah,
Okay.
yeah.
So if I have to, using this algorithm, if I have to predict the label for my X test, then what I'm going to do? I am going to look at the distance of X test with all the 900 data point, the
Yeah.
closest all the data point, and whichever 900 is closest, I'm going to assign that label to this point.
Hmm. Hmm. Hmm.
Correct?
Hmm.
This is okay.
Yeah, yeah.
Now, see, you need 900 neighbor, right? You need 900 neighbor, and maybe, and what you have is out of 1,000, 400 are labeled as 1 and
One.
600 are labeled as 0, right?
Hmm.
So let's say, for example, even if all the 400s are coming in this 900 neighbors, okay?
Yeah.
Let's say
Hmm.
all these plus 1 are coming. All
Hmm.
these are all 400.
Hmm.
Now I still need 500 neighbors, right?
Yeah.
Right?
500 will come from
So
600 group.
yeah, if all these 400 are already exhausted, this is the I mean this is extreme case. I mean, let's say all these 400 are exhausted in this 900, then
Hmm.
I still need 500 data points for which I need to check. I mean, which has to come in the neighbor, right? So maybe
Hmm.
this 500 will come from the label 0,
Yeah, zero.
right?
Hmm.
So
Hmm.
what does the algorithm say? You are going to take the
Okay.
majority vote. So in
Okay,
this
the
case,
zero.
the majority is definitely this label 0,
Yeah, yeah, got it. Got it.
right? That's
Zero.
all the
Yeah,
question says.
yeah, yeah, okay, got
Okay.
it. Got it.
Okay.
You
All
need to
right.
calculate
Hmm.
just statistic. Okay, thank you.
Okay. Yeah. Let's move to the next question. Okay. So again, this is true false question. You are given a training data set for a binary classification problem which has 100 points, 50 of which belong to class plus 1. Consider a KNN algorithm with k is equal to 1 that is used to predict the labels of the training data points. A point is considered as its own neighbor here. So based on this setup, you you have to decide which of these statements are true or which of these which statement is false. So first statement says the number of points that are misclassified by the classifier is 0. And the second statement says since the training error is 0, we have found a very good classifier for this problem. So you have to answer this. Is this one correct? So all that is given to you is that you have 100 points. Out of that, 50 belong to class 1.
Ma'am, S2 is false for sure.
Hmm.
Mm,
What about S1?
sorry.
What about S1?
S1. S1. I think it's false.
Okay.
Yes, ma'am, false.
So both S1 and S2 should be false.
S1 is true, I think, because we are not speaking about the test data, only the classifiers, no?
Okay. So you're saying S1 should be true and S2 should be false.
Yeah.
Ma'am, S1 should be false.
Okay. All right. Um, so here, look at the statement, look at this sentence over here, which says,
Ma'am, S1 is true because 50 is belongs to class 1, so 50 has to belong to class, the other class, right? The binary classification. So, but it doesn't say where it has been rightly classified or wrong. It doesn't say that. That we don't know. How can we comment then?
yeah, see, that's why, look at the sentence, in the question. It says, a point is considered its own neighbor. Okay. And we are talking about if a point is considered its own neighbor and the very first statement says the number of points that are misclassified by the classifier is 0.
So it takes its own label.
Yeah, so there is no I mean if if I'm talking about a 1NN algorithm, right? 1NN, where k is 1. So and we are also saying a point is considered its own neighbors. So any point we take, any data point we take, the first neighbor is going to be that point itself. And that label we already know, right? So the number of points that will be misclassified is going to be 0 because every point is its own neighbor, right? No?
Is this a valid question? Or is
This
it just
question,
a
sorry.
hypothetical, just come up with to probably play around with the words? Can there be an algorithm with can there be an algorithm with the k equal to 1? Everybody is right.
No, I mean, see, of course, 1NN is a valid algorithm, right?
How? You're
Why
comparing
not?
with yourself. No, you're saying that the one includes yourself,
No,
right?
this is a very simplest case of KNN, right?
Correct. The point is
Hmm.
considered as its own
Yeah,
neighbor.
okay. Okay, of
So
course,
everybody
it
is
is
zero
not
to
used
himself.
in practice. Of course, it is not used in practice, for
That's what
sure.
I'm saying. That's why I'm saying. So no, it really, when you really apply this, if
Hmm.
everybody is correctly
Okay.
classified, everybody is correct, right?
Hmm.
Every
No,
point is a correct point. Every point is
no,
a correct point. Correct?
correct. Yeah.
So the new point comes.
Hmm.
We don't know the classification. Correct?
If a new point come, okay, yeah.
It comes unknown, right? But
Correct.
I'm expected to compare it with itself, not more. Because
Correct.
it will remain as unknown, right?
That will remain as unknown.
So test is going to be completely useless.
No, see, here it's not about the practical of,
No,
I mean,
no. When we when we come up with the question, I want to see the integrity of the question. Now what I'm saying is, it the purpose is how we relate what we learn to apply it to problem solving. Now, if
correct.
I'm going to compare and make a decision with respect to myself, so I get 100 points and I go through the training process, I will find out every point is correctly classified from the training set. So training set error 0.
Right.
I don't bother about my neighbor at all. What I am right. He is completely classified. When the new fellow comes, he comes unknown, but he cannot compare with anybody next. Even if he is so close, he cannot, because he is the most closest and we are taking only one.
Correct.
So from that point of view, such questions really are going off tangent. It would have been 2 or something else. Maybe, I don't know what they really wanted to test, whether understanding of the people is clear or not.
No, here it's just about like, I mean, the very simplest case that is possible here.
No. Tell me what was wrong in the logic which I have said.
No, there's nothing wrong with the logic that I said.
So,
But
no. So what it means is we have got 100 points. Everybody has been declared to be correct.
Correct.
By the logic. Correct. By the algorithm. Now,
correct.
At the same time, any new test point cannot be classified. It will remain as what it was. Is that correct?
Wait.
No, you have 100 points.
Okay.
All of them
okay.
are classified in the training phase. Now you're saying the training is over. Now give me a test. I will check whether I'm correctly classifying or not. Okay? I'm giving you a point. But you are not allowed to compare it with anybody other than itself. So what will you conclude?
It is almost like the test guy is getting into the experiment uncontested.
One minute.
There is no contest.
No. Let me get a clarity on whether my logic is right. I'm saying the training is over. Now the test is come. One test point comes. But the algorithm does not check whether he is close to any of the 100 points. He is checking he is close to himself, which is true. What intelligence has been gathered?
Yes.
0 or 1?
It's basically that it's inconclusive, right? Like we cannot conclude whether the training error is 0 or
so
how.
The whole algorithm or the model that we have conceived is flawed. That is why I'm saying k equal to 1 is, I don't know where we will use it. K equal to one neighbor you can check, but then he is a true neighbor. Here you are saying you are also your own neighbor. That is the point which I'm taking an objection. Your point is considered as its own neighbor. In which case, k equal to 1 means that you are the only one who will be considered for any decision. You don't consider your neighbor. Is my doubt being understood?
No, your doubt is understood. I mean, there is not a problem.
Anyway, let us play around with the word, and then whatever is interpretation the professor had in mind, let us know that. Go ahead with the solution.
What is the right answer? S1?
Let's leave this question for now. I am not going to discuss this.
Let us see. Yeah, let us see.
Okay, let's do this question. So
that means no, statement
have,
answer was also there, no? What was the answer?
Let's skip this for now.
Okay.
So okay. So again, you have a class KNN algorithm and KNN classifier for binary classification problem with k is equal to 3. So you have a test data point which is 0, 0, and you have to predict the label for this point. Okay. Now there is a figure over here that I will show you. So there are 3 negative class, so which are marked on the diamond, right? So one is 0, 1, one is minus 1, 0, and one is 0, comma minus 1. And then there are three other points which are on the edges of the diamond except those vertices. So those points are here. That is, you can see the 3 points on the edges of this diamond that you see, okay? Now, the question here is, if you use the Manhattan distance metric, then what is the label that is your model is going to predict for the point 0, 0? And if you use Euclidean distance, then what is going to be the label? Just work out this problem. Any answer for the first part?
Ma'am, class negative. I'm not sure.
Okay.
Has to be class positive, right, for Manhattan?
Mm, okay. Did you find the distance?
Which is the test point?
0, comma 0.
0. Okay.
So you have to predict using both the distance.
And what is this positive class plus this plus sign
Uh,
indicating
Plus
class
sign
only?
is indicating the point which is labeled as positive.
Okay.
So this is approximately the plus sign where you see, right? This is approximately in the middle of uh, your 0, 1, 1, 0 line.
What is the convention for
Or
tie?
what is the convention for?
Tie.
Uh, you can write the tie. I mean, there is no convention given to you.
Okay.
Okay. All right. Let's see the solution. Someone mentioned plus plus. Okay. See if let's look at the second part. So if you use the Euclidean distance, then I can see here and I can say that the points which are labeled as plus, they are the closest to my test data point. And as I'm using k to be 3, so the majority vote is again going to be going to the point which are labeled as plus. So yes, for the second question, the answer is going to be uh, the label to be positive. But if
Ma'am,
you
which
look at
which points
first
are labeled as plus here? Which points?
these points, right? These are the
Point
points.
five, point five.
The cursor.
These points, right? Can you see this?
Okay, okay, okay.
These points.
Yeah,
So
yeah.
this point is at point 0.5, 1 by 2, 1 by 2. This point is at minus 1 by 2, 1 by 2, right? This point is at 1 by 2 minus 1 by 2, right? So
Okay.
these are the Euclidean distance is going to be the shortest for these 3 points from the test point 0, 0. So of course, this is going to be the majority is going to be positive. So this is going to be labeled as plus 1, the second part. But the first question where you're using the Manhattan distance, then what is happening there? So the Manhattan distance, we know that it is given by the absolute value of xi, uh, like it is going to be the absolute value, right? So you are going to look at the distance between 0, 1 and 0, 0. So it is going to be mod of 0 minus 0, which is 0, and mod of 1 minus 0, which is 1. So this distance you are going to get as 1, where this distance, if you calculate,
Which which
what
which
will you
distance?
get? Distance of this from this.
So it will be
Manhattan.
inconclusive. You can
One.
take either of them in that case. No?
One, no?
You
This
can
is
take
your
plus,
Again,
you can take
again,
minus.
this is 1, right? Again, this is
yeah.
1.
Both are
This
same. Both
this
are same.
So even
both are
this
same.
distance is 1, even this distance is 1,
Yes.
even this distance is 1,
So you
even
can
this
take anyone.
distance is 1.
You can take. You
Yeah.
can take anyone.
So you have three data points, which are, I mean, you have to take 3, but there are 3 positive and 3 negative. So um, unless there is some condition given, like in case of tie, how do you break it? It is unconclusive, right? So there should be some condition given to you here. So you cannot say for sure unless some condition is given to you, like how to break the ties. So first
So in
one,
that
you
in that
cannot
case, what
say
will be the
that.
answer of the first part?
So the answer to the first part is basically this is whatever information is given. Based on that, you cannot conclude. So it can be either of 2 classes. An exact decision requires information about how to break the ties. So that is not given to us. For the second one, it will predict us label positive.
Ma'am, go to the picture again. Graph.
Okay. Hmm. Yeah, here.
Yeah, distance. Here when we are calculating this, then you are getting the same distance, but physically it is showing this minus 1 0 point is distant from this. How
Hmm.
it is? Right, no?
see, looking at this, um, so
How it is
what you look
happening?
is the Euclidean distance. No,
No,
this
man,
is the
happened
Euclidean
distance.
distance.
Shrikant,
No,
Yeah,
Shrikant,
yeah, yeah.
let's
Euclidean distance is same. Correct.
look
this
at
is
the way how we will implement it as an algorithm. You got a test
Correct.
point. You have to
Mhm.
find the distance of that point with all the points.
Yeah.
You will compute. Here you have got 6 points. You have computed them. Then you are
Mhm.
supposed to sort it in ascending order. Then
Mhm.
pick the top. If the k is 3, you pick the top 3. Correct?
Mhm.
If it is
Okay.
5, you pick up the top 5. But the question here was, how do when we do sorting, if they are equal, in this case, all of them are equal.
Oh, yeah, all the equal.
That is where the confusion comes. So k and n is more like an elementary step. This is not practically used in most
Mhm.
of the practical applications. This is
This
for
is
the
the, the,
learning
the,
purpose. We are
the,
just figuring it out. Like a Humpty Dumpty sat on a wall is not something which we are going to use it every day. But in the nursery, we will introduce this to probably get the students familiar. So
Mhm.
KNN is the first step in all this classification. So we are going through some exercise. It is not going to be used in the real life.
Yeah, it is just to know okay, what are the issues with this KNN, right? So that we can
These
refine
are
it,
the
right?
issues.
Am I right?
No, no. Here, one very simple thing. When there is a tie, it is going to be difficult when you are
Yeah,
sorting, right? Number
yeah.
two, the moment the data becomes 10,000, for every data, you've got to keep comparing with all the 10,000 to
Yeah,
figure out where it is.
it's very very difficult.
There
Time
itself it goes out
complexity.
of.
Time complexity is there, right?
If you really look at it, there is no model here. It's only a procedure.
Hmm.
We are only blindly following a simple
Distances only.
procedure.
Calculations
Yes.
of distance.
There is, a model is supposed to give me some parameters. I can use it to quickly compute, right?
Hmm.
That is what the model is. If I'm given a table and if I find a relation that the second number is the square of the first, then I can throw the table and then keep the square as my formula.
Model, yes.
If I got to keep referring to number, whenever you give me a number, I got to refer to the
Here
table.
we are not getting the any model. We are
That's
just calculating the
so
raw distances and then comparing
these are the
our
three
model.
reasons this is not a popular. Yeah, but it nevertheless teaches the concept of classification. So every course will have this as an introduction, just to get an idea how classification gets done.
Okay.
Okay, don't pay too much.
Okay.
Yeah, we need
Okay.
to be checking all those things and then pick up the essence of this.
Yeah, yeah. You are right. When in
okay.
examination we have to do these such questions also. Right now, such questions we have to face. Right now.
Yeah, I mean, in
Okay.
exam, you can get certain
Yeah,
problems,
yeah,
right?
yeah, yeah.
Hmm.
Correct. Okay. Okay,
Okay.
ma'am. Please proceed.
All right. So the next model that we are going to see now for classifying for this classification is decision tree. So, okay. So here, what is our input? Again, the data set that we have, right? So this data set is x1 y1, x2 y2, so on till xn by n. Again, this xi's belong to RD, y's belong to label 0, comma 1. Now, if given this input, what I want is a decision tree. Okay. So my output here should be a decision tree. This is the output that we want. Now, what a decision tree look like is something, let's say you have asked a question. Now, either this question is based on this question that you asked, maybe you can classify whatever you have on two parts, right? For example, height is greater than 150 centimeter, right? So maybe it will again split into two parts, yes and no. Then again, you will ask certain question uh, whether height is less than this or something you will ask, right? So you have some question again, you will split into yes and no. So you basically are building a tree, and based on that, you're getting, um, you are splitting your data set in two part as yes and no. And again, you're asking the question, and at the end, you are going to get some label. So, zero, one. Let's say this is give you 1 0 1 0. So in decision tree, like in this, like what we want is if I'm given a data set, I need to construct a decision tree. I mean the model should give us a decision tree, and once we have this decision tree, we should be able to predict. I mean, given any new data set, what all we have to do after that is I take that data point that for which I have to predict the label and take it through all the I mean, uh, go through all the parts here and then decide uh, what label is the decision tree giving you for that data point that you have in hand. Right. So here you are learning this decision tree, where as in KNN you are not learning anything, right? So once we have the data set with us, we learn this tree, and then only using this tree, if I am given any new data point, I can get the label, I can predict the label for that data point using just this decision tree that we have. All right. So the very first question, I mean, the goes here. So this is what you call it as root node or the parent node also you can say root node or parent node. Then all these are all the questions that you ask here. So the question that you ask here, the question that you ask here, and maybe further after this also you would have asked a certain question. Maybe it didn't stop here, you asked some question, and then again it's split into yes, no, and then you come to a conclusion. So all these internal questions that you have asked, we call it as internal nodes. And the last prediction that you get. So this, um, these one, right? So this, they all are your leaf node. They are, the predictions are called the leaf nodes. So these are called predictions or the leaf nodes. Okay. So now the thing is that to build this decision tree, what we also need is the set of questions that you should have, which you are going to put in the tree, right? So,
So in this particular diagram, can we say we have
yeah,
got 5 prediction leaf nodes
5 leaf node, correct?
and
Yeah,
root nodes will be 3?
root node is only one.
Only one. Then what is this intermediate 2?
Eh, Uh, this is actually three, right? 3 questions you have asked internally. One
Yeah,
is
that's why it
this,
should be
one is
3 then.
this.
Yeah.
It is three. It is three.
Okay. Root node
Okay,
is
these
1
are
and
root
internal
node is
nodes
always one.
1
Root
and
node or
internal
parent
nodes are
node.
3.
Yeah, for this question, for this setup, yes. The three
Internal nodes
internal
are
questions you have asked.
okay.
And whatever comes at the end, they're called either the leaps or they're called the prediction. Okay. So at every stage, like whatever way you are coming up with this decision tree, at each step, the very first thing is you need to figure out what is the question that you're going to ask at every stage. So even to start with, you need a question, all right? So what is a good question? How do you decide what question should be asked at the starting? Or at every stage, what question should you ask that should give you a good tree, good decision tree? So that uh, like this characteristic of the question to decide which question is new is something that we give using this something called the information gain also, right? So I'll come there. So before we talk about how good the question is, uh, see, at every stage we are asking a question, and mm, you have the data set, you have this data set, right? And This is x1, y1, so until x and yn. Now you asked a question which is maybe fk is less than equal to theta. Okay, this is a question. This is a feature value pair. You asked this question. Based on this question, you are going to divide your data set in two parts. So if this satisfied, like the question that you've asked here, fk less than equal to theta, if this holds, then all the data set that goes here, let's call it as ds. And all the data point which goes for which it didn't satisfy this condition, let's call it d no. Okay, so in ds you will have set of some data point, and in d no you will have set of some data point. Okay, so
just one question: this DS and D no will be the last node, na? That will be the prediction node, isn't it?
No. This is not the last node. This is like after asking any question, you are going to split the data set, right? I mean, at any node. So I asked a question. It can be at any node, no?
Then the DS will subsequently become another next level of DS.
Okay.
It can go. It can branch. Can further go. Go down.
It will branch.
It will
It
go to
will
the depth.
branch.
Yeah.
Yeah.
Next branch will also come. There will be another DES.
So here we are
which
just
DES
talking.
will be taken?
No. Here we are asking about telling about just one. So this is where you're asking just one question, and based on the deciding yes no, this is something called a decision stump. Okay. So this is a decision stump that we have taken here, and for this question that is asked, this is either yes or no. Okay. So all the data point for which this condition is satisfied, I am putting it in ds, and all the data points for which the condition is not satisfied, I'm putting it in d no. That's all. Okay. Now
the question should be in such a way that it gives only two answers, either yes or no. The question is specific, because in some cases maybe the answer is not in the form of yes or no. It is different from yes and no. Then that question could not be implemented in this way in the decision tree, is it?
No. What did you ask? You asked the question should be
The
in such a
question,
way
the
that
question here
branch.
we put one question: this fk is less than equal to theta. This will just give yes or no, right? No problem. But some functions may be differently defined so that it does not give the answer yes or no. Then whether that function cannot be implemented in the decision tree, and such functions should be chosen that gives the result in the yes or no, only binary classification. Is it? What I'm thinking about.
See, this is not about binary here, right? I mean, you are asking.
I am thinking here it is only binary is here. If the question is not such a way that it does not give yes or no result, and different type of result is coming, then it cannot be implemented, that question. Suppose condition is there, if less than equal to theta, if the value of function, the variable of the function is in the range of 1 to 0 to 1 is different, 1 to infinity is different, -1 to 0 is different. Then the function will be different. No?
Shrikant?
Yeah.
There is no function here.
What is this fk? What is this
feature?
fk?
This is feature.
What did you understand so far?
Yeah.
That is a feature.
This is the value.
Feature. Okay, it has a value. The whole decision tree algorithm is on asking a simple question, not in the range of the type, whether the feature is above a cutoff or below the cutoff. That is
only two.
No,
the question.
That is a premises on which the whole decision tree algorithm starts. We could, as you said, that whether it falls within the range or not, those are all those complex questions can be built using a less or not. Am I right?
Okay, that is different. Here only
something has to be taken as the basis to build a structure. This structure is assuming the basis building block as we have features which are represented as numbers. Okay, they can be mapped into the numbers, and we are permitted to ask questions at every node whether that feature value is less or not.
Yeah, that is, we are just
Then
dividing the nodes to narrowing the search.
if
So
we
that
if we take this as the basic rules to build a tree, then we can build a tree to implement any logic that you have in your mind. So that is
one question here, theta, say fk feature k is less than equal to theta 1.
just checking. No, she is talking about how do we pick up the question. Correct? What should be the theta? That is the parameter, right?
That's a question,
So
basically.
yeah,
What should be
at
the
any
value?
point, okay, now any point, what is the purpose of asking this question? There was a data set before which comes to this and it divides into two groups, right?
Yeah.
Now, by asking this question, how much of information we have gained? If we gain more information, the question is good. Correct?
And if you further go down, we are going into the depth. For example, if k greater than theta, subsequently if DES is done.
Go to the second step. First, we should understand for this step where we are, what we are here for.
What I'm asking is, if fk is less than theta, subsequently after ds there is another fk. Say fk1, fk2, k2 less than theta 2, theta 2 maybe. So there will be another des.
You can build that structure, right?
Yeah, that's what I'm saying. I can build the tree like this.
Look, those are all, that's what I'm saying. You're going into the structure without understanding the basic component. We are now discussing how we come up and then build a component. This component purpose is only to divide the given data into two parts. Okay, the given data is a little hazy, and if the divided data becomes more clear, our question is intelligent. Correct? Assuming that given data has got 100 points, equal number of 0 and 1 labels. By my question, if I can separate into two groups, where in one group there are 70 plus, and in the other group 30 negative, then my question has added some intelligence, right? I'm able to discriminate. That is what she is now explaining in terms of how do we choose the theta that will help us to give that maximum differentiation in the output of those two different groups. The similar algorithm, we will keep developing it further down everywhere to the desired level, either in terms of a level or in terms of the accuracy. So let us develop a logic how we will pick up the theta, which will bring more information, which means asymmetry, symmetry. There is a method of information techniques. We have got to come with a metric to calculate what is the information content in a data set. Let us proceed now.
Yeah, thank you. Okay.
One question here, ma'am, out of this. Suppose X test is going through the decision tree. Question one comes about the X test data having the 5 features. Okay. 5 features. Suppose 5 features. Feature 1, feature 2, feature 3. In the first case, in the question 1, it is dividing. Either it is going to yes or it is going to no. If it is going to yes, then the whole feature will go to the yes. Again, the whole data set will go the X test data. One test data. It will go now in the yes. And then again, a question will be raised on that.
No, Srikant, okay. We are picking up an arbitrary K here. At any stage, this is the technique. Okay. Suppose you have got 100 data, it has got, each one has got, say, 3 subject matter.
I'm talking about only one data.
No.
This is only one data set, X test.
Fine, fine. One data has got a three characteristics, right?
Five, yeah, five,
Three,
five, yeah, five.
fine. You like
Three.
five?
Suppose three, no problem.
You ask about one question first. That question can only answer. I mean, question can be asked on one feature, one parameter, one comparison. That is the funda. That is why we say pick FK. You suppose you decide to ask the question on whether you have.
Suppose the house prices are there, a square feet, distance, or something.
Whatever is a feature, right?
Suppose three
The
features, yeah.
price is the price less than 5 lakhs.
Then it will go one side, otherwise that side.
That's
Okay.
right. Okay.
Yeah.
That doesn't prevent you to build that subsequently whether the price is less than 3 lakhs.
Yeah.
Nor it does not prevent you to ask from whatever collection you have taken, you can ask, is the school less than 2 kilometers? Okay. That is
My
no, look, that
question.
is how you build the whole thing. But right now, what she's trying to teach, explain is how we pick whether it should be 5 lakhs as the theta. Okay, suppose the given data is such, every data that you got is more than 55 lakhs. Okay, if that is the input given, I'm asking a question, is the price less than 5 lakhs? Everybody will come into no, correct?
The classification will be based on the questions being asked.
Wait.
The
Suppose
question should be.
if I have chosen theta to be 5, that question when is asked, if the is the price less than 5, every input will land up in no, correct? Which means the question is stupid. Obviously theta is not the right theta. So suppose if I ask for something, I ask, is the price less than 55 lakhs? Maybe some of them come to left and some of them come to right. Correct? Now we measure. There is a measurement of Shannon's theory coming here. How do we measure what is the diversity and the information content in yes answer and no answer? Put together, was it more than the original? So that we can say that additional information gained is due to the question. Then you try maximizing the information gain to find how the theta can be computed.
Yeah, the question should be so framed so that we can achieve our goal.
Questioning, we are going to find the theta. That's it, right?
Yeah, theta. That is the question, no?
Now we don't know how to figure it out. So we are driving,
Yeah.
we are driving and going through a method and mechanism and an algorithm to find how to find the theta, which will dissect the data into two more entropy. Then that may not be the end, so we can keep increasing it. So this is a building block. Okay.
Okay.
Don't look down. All you are saying, if I give 100 points, how do you segregate to have more information so that it can be very visibly seen? So what should be the question? That is what we are discussing now.
Okay, I think
Okay.
we have already discussed so many things over
Go
here.
ahead. Yeah.
So
that we can.
yeah. All right. So we need to figure out like whatever question you ask at every stage, you need to see how good is this question, right? So that aspect is given by here the information gain. The information gain. And like whatever feature value pair you have, like what is the information that you have gained by asking this question, right? So if you have a certain set of questions and for whatever question the information gain is the highest, I should be picking that question uh, for our node, right? So this information gain is given by the entropy of the data set minus some gamma time entropy of the data set which went to the positive side, I mean, for which this condition hold, plus 1 minus gamma times the entropy of Dino. Now, what is entropy here? And then another thing here is what is this gamma? So the gamma that you see here is nothing but what is the fraction of point that went to the positive, that went to ds, and 1 minus gamma is basically what fraction of data point went to dno. So this is just a fraction of data points that is in um, fraction of data point that went to ds.
DS.
That went to ds. Okay. So similarly, 1 minus gamma will be fraction of data point that went to dno. This is what gamma represents here. Now, what is entropy? So entropy, see, you have a set of label with you, right? You have this y1, y2, so on till yn. So once you ask this question, you have, how good is this question? Like if the question is splitting the data set in such a way that uh, all is going into one category, then in that case, the impurity is going to be zero. If it's correctly classifying everything, impurity is zero, right? So, but in general, this is not something that happens. So, how do you measure this impurity? So now, this impurity, like the if everything is in zero, uh, if everything is in zero, or if everything is in one, then in that case, this entropy, this impurity is going to be zero, right? I mean, what is this? What do you mean by this zero and one here is that if if you have if you have asked this question and asking this question, it's splitting the data set in such a way that everything falls into the same either DS or D no with the same label, then in that case, the P here, that is the probability. I mean, the fraction of, the fraction of one that you have in data set or the fraction of zero that you have in the data set. If this is zero or this is one, in that case, this is going to be, the impurity is going to be zero. So this y-axis here measures the impurity. But at the p is equal to half is where this fraction is going to be, this impurity is going to be the highest. So when you plot the graph, right, this is, it's going to look like something like this. Okay. So this is a symmetric function where the highest impurity will be at a point when p is equal to half. So p is equal to half means the fraction, half of the data set has this label 0 and half of this data set has label 1. So in that case, you have the impurity to be highest. And if this is the graph that
This
means,
half is the entropy.
no, this entropy. This is half is not entropy. Half is p. This
What is
is the
entropy?
entropy.
What is entropy exactly?
So this is a function, the measure of impurity, right? So this function, this graph that you see here, right? So it is given by this entropy function.
And how it is defined?
So there can be, I think, many function which can give you a certain the structure. So the entropy function, the way you define, you can plot this also. You can write in some Desmos or GeoGebra or somewhere. So entropy of the labels is given by minus of p log p and minus of 1 minus p log 1 minus p.
Yeah, it is given in the lecture, but how it is?
You can plot if you try plotting this, right? Plot it somewhere. And you can see the structure is like this. The structure is going to be like this for this function. And this is the entropy function.
Of course, the log function will be like this only, because log is the only concave function.
No, log, if you plot log x, is not going to look like this. I'm saying plot this entropy, and you will see it has a structure like this.
Okay. Okay. Yes.
Okay. So this is the entropy function.
Is it derived function or something already predefined? How it came? This P
Um,
like this. Yeah,
how it
something
came,
black,
see, it
some black
just
box.
not some black box. I mean, we looked at the shape the impurity is taking, and this shape is easily defined by this function that we have written over here. Maybe there
Okay.
are other functions that can also hold
Okay.
true for a graph like this, but
Okay. Got
this is what we're using it here.
it. Okay.
So depending on like how much information have you gained, I mean, depending on which question is giving you the highest information gain, is what question you will choose at each node of the decision tree. Okay. Um, okay. Maybe let's do some problem from decision tree. Um, or then we will see
But
this.
the graph would be same if we take entropy instead of impurity in the graph.
No, we have taken impurity only, no? I mean, we were looking at impurity. At 0 and 1, the impurity is going to be 0. But
But the graph
at
would be the same if we take the entropy.
the graph will be same if we take impurity.
Entropy instead of impurity.
I mean, we are plot this function. Okay, this function is entropy function, so you can write entropy here, no problem. Entropy of P. This is entropy of P. Okay, so this is one question from decision tree. Here it says for a decision tree, each node has exactly two child nodes, which is called which we are calling it as a balanced tree. So if a tree has a depth of 5, how many leaf nodes are going to be there? So at each node you have two child nodes. So if this is a question, I see a hand raise. Oh, sorry.
Is it 2 power 5?
Yeah, it is 2 to the power
It is
5.
it
Yes,
2 to the
ma'am.
power 5.
32.
Yeah. So everybody is clear about it?
Yeah, yeah. It is okay.
Okay, okay. Yeah, good. So yeah. So basically, like if you have just tree of depth 1, you are going to get 2 leaf node. When you have a tree of depth 2, so you are going to get 4 leaf node. So it is just growing exponentially with the power of 2. So if you have a tree of depth 5, it is to the power 5, which is 32. So there are going to be 32 leaf nodes in this case. All right. So here you have the decision boundaries plotted for two different decision trees. Uh, the question says which of the two trees is likely to perform better on the test data. So
Test
what do
one.
you think? Test one, okay.
How it is?
Because
So,
it's overfitting.
yeah, that's correct. Uh, so the tree, what you're seeing here are the decision boundary for tree one and tree two. Now, if these are the decision boundaries for tree one and tree two, the question that is asked is which of these, like if I'm given a test data, which tree is going to perform better? So if you look at the first tree, I mean the it is um, I mean it is dividing the question that it asks. The decision boundaries are quite clear, right? On this side, okay. So here it's everything is labeled as negative. This is all positive. This is all negative. Here it's all negative again. Uh, and here you have a mix of positive and negative in the middle portion here. Uh, but it's okay. If you look at the second tree, here you have overfit the data. You are trying to make the training error to be exactly zero. So you're overfitting it, right? So if you get some data point in this which falls here, then you're going to predict it as negative. So basically, in tree two, you are overfitting uh, your data set, overfitting the model. So it is not going to generalize well if you get any new data point. And if you have to predict for that new data point, it may not work very well.
Ma'am, can you please explain even how we are overfitting in the trade two?
Um, see here, see in tree two, I mean this is uh, here. This is all fine. This is all fine. This is all fine. This is all fine. Okay, but if I look at this portion, I look at this. If I look at this portion, then you have this red label point, which is here just one point, right? And this is all. This is one. This is like this is a boundary that you have given. Then for this point that you have, again for this, we have a boundary over here, right? Which is not required. I mean, are you able to see what I'm annotating?
No,
Not
no,
sure
no.
if it's not visible.
Very visible. What
Is it visible?
you? Yeah, I know. Yeah, just
It is visible, no? Okay. Yeah. So by drawing the boundary for each of the point here, I mean, we could have left it like just like this. But by drawing the boundary, uh, by making sure the error turns out to be zero, you are overfitting it, right? You're I mean, you're also fitting the noise here.
which one is noise?
So,
Shrikant?
Yeah.
Okay, consider these two separate algorithms. Algorithm, we ran it twice. First one stopped at tree one. How many questions we had? 1, 2, 3, 4 questions.
1, 2, 3, 4 questions.
Right? It stopped.
Yeah.
The second, maybe I ran that algorithm and I want little greedy, so I went maybe multiple level, 8 levels or so. Correct?
Yeah.
I come with the algorithm saying tree 2 is the best algorithm. 8 questions, everything is accurate. What is my training error?
0.
0. What is your training error?
Training error.
2
here you have training error, right?
Training error.
Yeah, this is the training.
Correct. So you have a training error which is non-zero. Correct? You have compromised your training error, thereby allowing a tolerance. Now, suppose we both have our own algorithms. Nikita comes with the new data. It is in this zone, what she has drawn, very close to the red point
In T1, in T1.
in T1,
Yeah.
right? So
Yeah.
your algorithm will say it is green. The label is green, right? I don't know what convention we use.
Yeah. Yeah.
In general perception, that is the right approach. Correct? We know the red point there is a outlier.
The red point is outlier, yeah, because it is too.
So, but though he being close by is ignored because it falls into that block bucket, he will get it classified as a green. Whereas if the same point given to me in my algorithm, it was so greedy and sticky, it will be falling within that, and I will say it is red. Test error will be high. You get it? So, though I have passed in all my GAs and assignments, I fail in quiz or in real life.
Real life.
Whereas you have been little tolerant, accepted those outliers to contribute to your error, but you will perform better. You get it? This is a contradiction between training error versus a test error. When we
Yeah, in the T1, a space has been given. Yeah, yeah.
This is exactly the whole concept of the machine learning, all those deep learning, everything will come in. We discover from the past and don't cling it to that and saying that I have understood everything.
Yeah, there is a space to.
So bring in your whatever lambda or whatever is the learning rate and then error rate, ridge.
Or hyper parameters, all the hyper parameters.
Those the words are different, but basically you allow that. Don't go only to minimize your training error. That is what the phenomena or the tendency to fit what we know is called overfitting.
Overfitting is not good. Yeah.
That's what we did now. Right?
Yeah.
That example very clearly says it's overfitting. From that, anyway, one can say tree 1 will be better.
Okay. Okay, fine. Thank you.
Okay. All right. Um, Moving to the next question. So here it says the data set at node Q has 1000 points. And after you ask this question Q, it splits into two parts where 200 points goes to node L. So here 250 points goes. And in a node R, you have 750 points that are there. So what is the value of gamma over here? So this is gamma, okay, not Y, gamma.
Point 0.25?
Yeah, 0.25 is correct. Because gamma is just the fraction of points that goes to ds divided by the fraction of point that goes to ds uh, the cardinality of ds by total d, right? So that is what gamma is. So the gamma will turn out to be 250 divided by 1000, which is 0.25. Yeah, so this is a simple question. The next question is where we're going to use this. So in the next part, you have um, you have to basically find the information gain. So you have this data set X that has X point. Now all the points in D are made to answer this question Q. The answer Q can either be yes or no. dy is set of all points for which answer to question is yes, and dn for which the answer is no. There are two labels, 0 and 1. Uh, there are 60 points with label 1 in D, and there are 36 points with label 1 in dy. Okay. Then there are 12 points with label 0 in dy and 8 points with label 0 in dn. You have to find the information gain for the question Q. So you have a question Q here. Now you have asked a question. Based on this, you are dividing it into yes and no, right? There are 60 points with label 1 in D. So in D, you have 60 points, that is label 1, and 36 points with label 1 in dy. Okay, so this is dy, and if this is label 1 and if this is label 0, 1 is how many? 36. This is 36 is what we are saying. Okay, there are 12 points with label 0 in dy. These are 12 points. All right. There are 8 points with label 0 in dn. So in dn, you have 8 points with label 0. All
Yeah.
right. Now you have, these are the information that are given to you. Now, using this information, you have to find the question that you have asked here. What is the information gain? Um, or what is the information gain? So before you start finding the information gain, you need to know what is your gamma here. You need to know what is the distribution of data points in this DS and DNO. So basically, how many are classified as 1, how many are classified as 0 in both these sets. Original data set, how many were 1, how many were 0. These all information is something that you have to know. So just by just giving this information, can you tell me how many data points have label 0 in D?
40.
40 as label 0 in D.
40.
Are you sure?
Okay, it is not the percentage, no. Okay.
No, I'm asking in the data set, uh, all that you have is there are 60 data points with label 1. So how many has label 0?
X minus 60, right?
X minus 60. What is this number? Can you get that number? Can you get that number using the information that is given to you?
Is it 20?
Here it is 20, right?
Yeah,
Because
20.
in DS you have 12 data points with label 0. In Dino, you have 8 data points with label 0. So overall in data set, you have 20 data points with label 0. So your data set has 80 points, where 60 of label 1 and 20 of label 0. Okay. So if 60 is of label 1, I know what is the number. I can tell what is this number going to be. This is going to be 24.
24.
Okay. Now you have all the information that was required to calculate the information gain. So you need to calculate the entropy for all this, entropy for D, entropy for uh, DS, entropy for D no.
What entropy for D is 60?
Entropy for D is 60.
No, what is this? What is
What
the
is
entropy?
what is the entropy?
That's what I'm asking. What is the entropy D?
Okay. Okay.
Total. You can add both.
Mhm.
We should add both.
So yeah, I am giving. Yeah, here you can see
80.
entropy.
80.
Uh, entropy
B.
formula here.
Yeah, give me the formula. Okay, okay, okay. P lab. Okay,
Hmm?
P. Right. Entropy of P. Right.
So I will tell you what is this value that you will get because see if, first of all, what is P? P, can you tell me what is P for this question?
P is D.
P
60
should
by
be
80.
0.4.
P is
P is
60 by
60.
8,
Yeah,
right?
0.6.
Not point
60 by
0.6.
8.
अच्छा 80
60.
total अच्छा हाँ
3
Okay,
by
okay.
4,
60 by
0.75.
60 by 80.
60 by 80 because this is a fraction of data point with label 1, that is 3 by 4. And once you know this, you can easily find the entropy. So I will, let's skip the, I mean, you can do it yourself later. I have the solution, so I'll just go
Yeah,
through it.
please. Yeah, please. So
So one
you
more thing.
shared
So,
you shared this yeah, slide.
I'll share the slide. But now,
can
see,
you show the next
entropy,
slide next page
wait. So this is about entropy of P, and you told me what is P. Now coming to DS, this part.
D, yes.
Yeah.
D, yes
So
is
coming to DS,
60. D, yes is 60.
no, DS, in the DS now, tell me
The
what
P
is
will be
P
36 by 48.
36 by 48, right? And what is going to be gamma? What is gamma?
36.
36
Gamma is
by
36?
36 by 80.
Oh, okay.
No, I'm
Gamma is
asking
36
gamma.
by 48. Oh.
What is total? Let's see, 36 by 60.
36 by 60.
Am I right?
Thirty-six by 60 or 36 by 48?
36 by 48. For that level only we have to see, no?
No, I'm asking the gamma.
Gamma is your D, yes. Mode of D is divided by mod of D. Mod of D, what is D here? D is 16.
36 by 60
Am I right? 36 by 60. It should be 60. .6. 0.6.
So gamma is the fraction of data point that went to DS side. So DS, how many data point went? 48, right? And what is the total number of, what is the cardinality of data set? 80, right?
What was the DS? DS 36 was in DS and okay, yeah. In the level 1, yeah. It was 48.
So DS is cardinal fraction of data point that went to D, yes. So in this case, in DS, you have 48 data point,
Correct.
and
40,
total you have 80. So it
48
is
by 60.
48 divided by 80, not 60, 80, no?
80.
Gamma,
Because
gamma,
60 is 60 is level 1.
gamma. Yeah, okay.
And yeah, and 20 is level 2. Correct.
Okay.
What is the question
I'll
being
just,
asked? We have to find entropy of D, no?
you have to ask the information gain by asking this question Q. And how will you find it? You will find the information gain uh, is what is the entropy of D minus the proportion of data point that went to DS times its entropy plus the proportion of data point that went to DNO times its entropy. Right. So, um, like, yeah, that is the information gain. That is how you find the information gain. So we found the entropy for D here, which comes out to be 0.811. We find the entropy for dy, which turns out to be again 0.811. And we find the entropy for dn, which again turns out to be 0.811. So when you find the information gain, it is actually 0.
So the question is not properly
It's not
chosen.
a good question. Yeah.
Okay.
So you're not,
By this question, we do not get any information gain, right? 0.
yeah, no information gain
If
is there.
anything more than 0, then there is a gain, isn't it?
Yeah, then there is a gain here.
If anything,
So,
if it is anything, whatever, it basically is a percentage. So entropy D minus, say gamma entropy D ES minus 1 minus gamma entropy DN. If this figure is say 0.2, say for example, then can we say it is 20% improvement, information gain?
Yeah.
You can say that, no? Because
Yeah.
there are percentage numbers.
This will also
So,
always come positive, no? Always positive it will come between 0 and 1.
it will come out to be positive. Yeah.
Yeah. We will calculate accordingly. Following this. Good question. This is a good, very good question.
Okay. So, yeah. So about calculating, I mean, if you have to, if you're given a question and if you need to find out the information gain, this is how you can do it. But you need to be very careful of the data, I mean, that is given to you, right? Like for in this case, in this question, you need to um, look at, I mean, you need to know at each step what is your like how many data set in the data set, what are the labels and
Ordinality of the DS and DY and
yeah,
D.
what ds dy, and in ds dy, how is the distribution of the labels, right? All that you have to be very clear. But once you know clearly all these things, then it's just calculation.
Concept, just if you understand the concept, then calculation is easy, but concept is more important, right? You will do it, ma'am. Calculation, you will do again.
Yeah, you
By
can do the
doing.
calculation. Yeah.
You will do it.
Okay.
Okay, ma'am.
All right. So this was the last question. Yeah.
So that we are going to close it now.
Yeah, we are going to close it.
Okay. Okay, ma'am. Good night. Somebody is waiting.
Yeah.
Thank you.
Thank you.
Yeah. Thank you.
Thank you.
Yeah. Thank you all.